We now look at the question of when a finite extension is simple. In particular, we will prove that any finite separable extension is simple. So in particular, any finite extension of the rational numbers is a simple extension. So let's begin by recalling that an extension E containing f is said to be simple if E is generated over f by a single element alpha in E. The first result is the quite surprising result that a finite extension is simple if and only if there exist only finitely many intermediate fields between E and f. Let's begin by proving that by assuming that there are only finitely many intermediate fields and proving that the extension is simple. So E is certainly finitely generated over f, and an easy induction argument tells us that we only need to prove this result when E is generated by a pair of elements of alpha and beta over f. Let's begin with the finite case. If f is finite, then so is E, and the multiplicative group of non-zero elements E star is therefore also finite, so by a previous result it must be cyclic. If we take a generator gamma for E star, it's easy to see that E is equal to f of gamma because all the non-zero elements of E are just powers of gamma. So let's move on to the case where f is infinite. In this case, consider the fields generated by the elements alpha plus c beta, where c is in f. Obviously, there are infinitely many choices for c because we've assumed that f is an infinite field, but there are only, by assumption, finitely many intermediate fields. This tells us that a lot of these f alpha plus c beta must be equal to each other for distinct c, for different c's. So in particular, we must have a pair of distinct elements c and c prime in f such that f of alpha plus c beta is equal to f of alpha plus c prime beta. But then this field contains both alpha plus c beta and alpha plus c prime beta. And a simple elimination argument tells us that beta has to belong to this field, so alpha belongs to the field. So f of alpha plus c beta is equal to f of alpha beta as required. So that shows that if there are only finitely many intermediate fields, then the extension is simple. Let's now prove the converse. Let's suppose that the extension is simple, and we will deduce that there are only finitely many intermediate fields. So let K be an intermediate field. Let m of alpha x be the minimum polynomial for alpha over f, and let's look at m alpha k, the minimum polynomial of alpha over k. Then we certainly know that m alpha k divides m alpha. Let's suppose m alpha k is monic with coefficients c0 up to ct minus 1, say. And let's let L be the field generated by these coefficients. We claim that L is actually equal to k. Well, L is certainly contained in k because all the coefficients, all the ci's, belong to k. But let's also notice that the minimum polynomial of alpha over L, m alpha L, has to equal to m alpha k, because the minimum polynomial couldn't have smaller degree, because if it did, it would have coefficients. The smaller degree polynomial would have coefficients in L, which is contained in k, and this would contradict the minimality of m alpha k. So these two polynomials are the same. But what does that mean? Well, E is certainly equal to the field generated over k by alpha, and similarly it's also equal to L of alpha. So the degree of E over k is just the degree of m alpha k, and similarly the degree of E over L is the degree of m alpha L. But these two degrees we just noticed were the same. So since L is contained in k, that tells us that k is equal to L. Thus, any intermediate field is generated by the coefficients of a monic divisor of this fixed minimum polynomial, M alpha. But there are only finitely many such monic divisors, so there can only be finitely many intermediate fields. Let's now use this result to prove our main theorem that any finite separable extension is simple. So suppose we have a finite separable extension. So E is finitely generated over F, say by alpha 1 up to alpha n. What we do is we take the normal closure of E, show that that is normal and separable, and hence there are only finitely many subfields by the fundamental theorem of Galois theory. So what's the normal closure? Let's let mi alpha be the minimum polynomial of alpha I over f, and let k be the splitting field over f of the polynomial, the product of these polynomials. By definition, k is generated by all the roots of these mi alpha, and these roots are separable because the alpha I are separable, which exactly means that their minimum polynomial doesn't have repeated roots. So the mi alpha don't have any repeated roots. So k is generated by a set of separable elements, and that implies that k is a separable extension of f. So the normal closure of a finite separable extension is again separable. So we have an extension k of f that's normal and separable, so it's Galois. So the intermediate fields correspond to subgroups of the finite Galois group, and obviously there are only finitely many of them. So there are only finitely many intermediate fields between k and f. In particular, there's only finitely many between E and F. So by the previous theorem, the extension is simple. So let's just stress one trivial corollary. That's that any finite extension of the rational numbers is a simple extension. Finally, let's just sketch a basic example of a finite extension which is not simple. Clearly, it has to not be separable. Let's take an infinite field of characteristic P, and let's let E be the field of rational functions in two variables y and z, and let's let E be the subfield of rational functions in yp and zp. We claim that E is not a simple extension of f. First, let's notice that the degree of f of y over f is p because the polynomial x to the p minus yp is irreducible by Eisenstein's criteria. And similarly, we can show that the degree of E over f of y is p, so the total degree of E over f, not surprisingly, is p squared. Now, take any element c and k, and recall there are infinitely many choices of c. Y plus cz to the p is equal to y to the p plus c to the p z to the p, because we're in characteristic p. And that's in f, obviously. So the degree of f of y plus cz over f is less than or equal to p. Now, suppose that for distinct c and c prime, we had that two of these fields were the same. Then, as in the previous theorem, an easy elimination would then tell us that f of y plus cz contains both y and z, so it's equal to f of y, z. But now we have a contradiction because this is E, and we've already shown that the degree of E over f is p squared, and the degree of this field f of y plus cz over f is p. So this is a contradiction. So we can't have a pair of distinct elements of K giving us the same field. So whenever we have distinct C and C prime, these two fields are different. So there are certainly infinitely many intermediate fields of the form f of y plus cz between f and e. So by the first result, we proved the extension cannot be simple.